Hi everybody, welcome to week 8. This week we're going to be looking at linear methods and in particular support vector machines. So we'll be looking at three main topics today. First off, linear discriminant functions, which is a really simple approach to doing classification, and then we'll build on that some ideas to get towards support vector machines. In the middle we'll be looking at kernel methods. Kernel methods are a newish kind of approach towards doing classification and a whole lot of other kinds of things. And one specific kind of kernel method is a support vector machine, which is the classifier that we'll be looking at this week. So first off, let's look at linear discriminant functions. So we can define a linear discriminant function as just a function that can separate two classes of data. And we have a function here, so y, which is sort of a value of essentially where we're going to classify, is a function of g of x. X is the vector that contains the data item. And g of x is defined as some weight vector w times the x data vector plus w0, which is called a bias. So the weight vector transpose times the x gives just a scalar, a number. Adding on the bias gives another number. So if that number is greater than 0, then we assume that x is in class 1. If it's less than 0, then we assume that x is in class 2. And if it is equal to 0, then that means it's on the boundary between the two classes, so the decision boundary. And we don't know whether it's in class 1 or 2. So what we need to do with the discriminant function is work out what the values of w0, the bias, plus all of the weight values, so w1 all up to wk for however many dimensions of data we're looking at. So this wx plus w0 forms a hyperplane that separates the data. So in 2 dimensions, a hyperplane is just a line. In 3 dimensions, it's a plane, so a flat straight surface that separates the two different classes. So the w vector gives the orientation of where that hyperplane is, and w0 gives the location of the hyperplane away from the origin. And w0 divided by the length of w gives the distance from the origin. So it helps if we can see a picture to show what's happening. So we can see here just an example in 2-dimensional space. So we just have an x1 and an x2. And you can see we have our red data points and we have our blue data points. And we're going to separate the blue from the red ones. So we want to find a line, g of x, that separates the red and the blue. And you can see we've found one. And that g of x equal to 0 is where that line is. So for g of x less than 0, it equates to the red region of the graph, and g of x greater than 0 equates to the blue region of the graph. So you can see that if for a particular new data point, our g of x is more than 0, that suggests that it's in that blue region of the space, and that it should be a blue dot. So w is a vector that says the orientation of where that green line is, the hyperplane is, and w0 divided by the norm of w, or the length of w, gives us the distance that the green hyperplane is away from the origin. So in a nutshell, that's what we're going to do. And we need to find out how to set the w0 and all of the w values so that we can get the orientation of the green line at the right angle and then also the right distance away from the origin. This is just a very simple case where we only have 2 classes, but it turns out that this scales up to a multi-category case pretty easily. And the way it does it is by making the multi-class classification into a whole lot of single-class classifications. So if we had 3 classes, we'd have class 1 versus class 2 and 3, class 2 versus class 1 and 3, and class 3 versus class 1 and 2. So we make the 3 classes into 3 different classification problems. And when we solve all of them together, we can work out which class the data point should be. So to make this method work, we need to work out what the values of W and W0 should be. And that's in essence the parameters that we need to fit to work out how to build the classifier to separate the blues and the reds. So one way that we can go about doing that is by minimizing the sum of squared errors. And we'll see how we can do that in a minute. We can also eliminate that messy W0 variable by including it in W and adding an extra X0 value, pretend X0 value of 1. So we make the number of dimensions 1 more, but by doing that we can make the maths a bit tidier, and we'll see how that happens in a minute. Now, you saw earlier that we're separating the red dots and the blue dots by a straight line. So it's really important that we can separate those 2 classes by a straight line. Otherwise, it's not a linear discriminant analysis. So this has a name, and it's called linear separability. So if the data from the 2 classes can be separated with a hyperplane, then the data is said to be linearly separable. So if that's not the case, if the red and the blues can't be separated with a straight line but with maybe a curved line, then linear discriminant function can't be used to classify the data with no errors. So this linear separability is an important topic. Well, it's very important for linear discriminants, but it's also an important topic in neural networks, which we're not going to talk about neural networks in this lecture, but it's also useful in support vector machines, which we are going to talk about. We can think of that weight vector W as specifying some point in a weight space. And we can move the point in the weight space around, and that equates to different positions of that green hyperplane. Now, because of the data points that we have in our training set, they constrain where the weight vector can lie. That separates the data. But it turns out that even where you have your X set, there can be many possible separating hyperplanes. So we need to work out some way to choose the best one. There's 2 approaches to this that people come up with. One approach is to choose the hyperplane that maximizes the minimum distance between the samples and the line, and that's what we're going to use slightly here. There's another better approach that uses something called a margin, and that's what support vector machines use, and we'll see that a little bit later. But first off, let's look at the one that maximizes the minimum distance between samples and a line. And the way that we're going to do it is to use the method of least squares to choose the hyperplane. The method of least squares looks like this. So we want to find the weight vector that leads to the minimum sum of squared error for the patterns in the data set. So let's pull apart this equation. So E is the error. So the error for the weight vector, because the only thing that can change in this, in what we're doing, is the weight vector. The x's are all defined. So we're going to have an error on the weight vector, and let's ignore that first part. So inside the brackets, we've got y of n xnw. So all that's saying is that's the output for pattern n from the hyperplane using the weight vector. So that's going to be that the g of x. So we subtract. So it's either going to be a plus 1 or a minus 1. So we're going to subtract Tn, which is the target value for the pattern, and that's going to give us an error on that one pattern. Because that can be either negative or positive, we need to square that error, and then that's going to be a sort of a squared error on the pattern. So if there's no error, if y of n xnw is the same as the target, if it's what we expect, then that bit inside the brackets is going to be 0, and it doesn't contribute to the error. But if the value isn't correct, if the predicted value isn't correct, then that number's going the number inside, when you square it, is going to be a positive number. It's going to contribute to the error. So the bit on the right is the error for that pattern n. We're going to sum that up for all of the patterns, and then we're going to divide by half. Don't worry about that. That's just really to make the maths a bit easier in a minute when we take the derivative of it. So what we've just got here is the error for the particular weight vector. Now what we want to do is to find the weight vector that minimises that sum of squared error. And the way that we can do that is using something called gradient descent. The idea is that we're going to change the components of the weight vector a little bit in the direction that minimises the error. So we're going to go, it's gradient descent, we're going down the hill. So we're going to change W in the direction that minimises the error. And we're only going to move a little bit in that direction, because if the surface is quite curved and bumpy, then we may not want to go all the way in that direction. We might need to take small steps. So we have an algorithm that looks like this. It's quite a straightforward loop. So let's see what happens. So we start with a random initial value of the weight vector. Then we're going to have a loop that just says we're going to change the weight vector by some amount. We'll talk about that bit in a minute. So we're going to change the weight vector by some amount until the amount that's updated is less than a threshold. So we're going to keep on doing it until we only move by a small amount. Now let's look at how this weight's updated. So that weight tilde says the new version of weight tilde is the old version of weight tilde minus some amount. And the some amount is, let's look at it carefully. So we're taking the derivative of the error with respect to the weight, so the change in error with respect to the weight, evaluated at the current position of the weight vector. So the change in error with respect to the weight is going to give us the direction that the error increases. So we want to go in the opposite direction of that, so that's why we have the negative. And the eta is there because we only want to learn at a small rate. So that's usually a number between 0 and 1, and usually it's a fairly small number, so maybe 0.1 or whatever. So what we're saying is the new version of the weight is the old version of the weight minus some learning rate times the direction that where the error increases with respect to that weight. Because if we go in the opposite direction, that's the direction that the error decreases. So that's one way of finding that position for the green line. Let's talk now about kernel methods. So kernel methods are currently a fairly hot topic in machine learning, and it's a whole set of associated approaches that sort of soup up some linear methods to make them work on nonlinear patterns. And there's a whole lot of methods that can be used for supervised learning and unsupervised learning problems, but we're going to look at just one method, and that's support vector machines. And support vector machines are classifiers. Essentially they're linear discriminants, but made to work in a nonlinear way. This is a sort of a schematic of how kernel methods work. And let's look at each bit in turn. So at the start we have our data set X, and we apply some kernel function to produce something called a kernel matrix K. And the kernel matrix has is a square matrix. It has the same number of rows and columns as there were original data points in the data set. So it gets rid of the dimensionality of the data. And each cell inside the kernel matrix you can think of it as a sort of a similarity between data points. So each cell is derived by calling a kernel function on two data points. So what the kernel function does is it's used to transform the data from the original data space into something called a feature space. And typically the feature space is much more highly dimensional. So the transform point, instead of being x, is phi of x. Generally it's a nonlinear function, and the kernel, this kappa, the kernel function, so we have a kernel function that takes data point x and data point z, and what it is the dot product. That's what those two braces, angle braces mean. So the dot product of x and z that have been transformed into the feature space using that phi. So conceptually, you've taken x, transformed it into the feature space, taken z, transformed it into the feature space, then you take the dot product of those, which are going to be two high-dimensional vectors. We take the dot product of those two high-dimensional vectors, and that's going to give a scalar, and that's the number that will then go into the kernel matrix. And you can think of that kernel function as a way of modelling a similarity between data points. Typically, though, we don't need to do that transformation into the high-dimensional space using phi explicitly. We sort of combine the phi and the dot product together, and we can sort of cheat and get that scalar straight away. And that's important because the feature space could be quite crazy. It could be like an infinite dimensional space. So depending on what kind of phi we use or what kernel function we use, we can get quite different effects. Here's an example of two kernel functions. The first one is called the linear kernel, and all it is that it's the case where phi does nothing, where phi of x returns x. So here we're just taking the dot product between x and z, and that's a form of similarity between the data points. It's sort of like the cosine similarity between the data points. So in this case, the feature space is the same as the data space, so we're not doing any transformation there. More typically, people use something called the Gaussian kernel, or it's often called the RBF kernel, for radial basis function kernel. And there, to get the kernel function between data point x and z, we take the distance between x and z, which is what the norm, we square it, divided by some 2 times sigma. Sigma is it emphasizes the kind of distance between the data points. It's sort of like a radius of effect or a range, and then we raise that to the power of e. And this is a nonlinear kernel, and in fact the space, the dimensionality of the feature space is infinite dimensional in this case. Gaussian kernel is often what people will use for support vector machines. So there's a whole range of kernels, and some of them allow the data point, the x, to be something that isn't even a vector. It can be text, it can be strings, it can be graphs, it could be lots of different kinds of things. And this is quite important because it means that you can use the kernel, as long as you've got the right kernel function, you can use a whole set of algorithms, support vector machines, a whole lot of other kinds of things like kernel principal component analysis, other methods, and it doesn't care about the data type that you use. It can be text or strings or graphs or vectors, and as long as you stick it through an appropriate kernel function, you can still do the pattern analysis. So going back to our schematic, we've got our kernel matrix now. The next thing we do is apply our pattern analysis algorithm. And again, it doesn't care really what the kernel function is. And after we apply the pattern analysis algorithm, we get some kind of result. So it might be a classifier in the case of support vector machine, or it might be some kind of visualization, or it might be kernel PCA or something else. So there's lots of possibilities for this pattern analysis algorithm, but the effect is that the bottom line is that they all accept some kernel matrix K and use it to analyze patterns. So a support vector machine uses K to classify points into two classes, kernel PCA uses K to visualize data. Kernel K-means is like a non-linear version of K-means classification, which we'll talk about later in the semester. There's also other algorithms that allow you to do regression or outlier detection or other kinds of things. So in a nutshell, that's what the kernel methods are about. So let's look specifically at just support vector machines. So I'm going to follow the treatment that's used in Witten and Frank here. Witten and Frank are the guys that wrote Weka, and they wrote a very nice textbook that's really quite straightforward and easy to understand. So I'd really recommend that if you want to get a down-to-earth description of how support vector machines work. So support vector machines are sort of a blend of linear modeling and instance-based learning, and they're a binary classifier. So we can extend it to multi-class problems like we looked at earlier and regression, but we're just going to look at binary classification. The idea with support vector machines is we select a small number of critical data points, and then we build a linear discriminant function that separates those data points as widely as possible. So the trick is to choose the critical data points. And what's quite special is that we can ignore all the other data points. We only really care about these critical data points. So just going back to remind you about the linear discriminant. So we're looking for this green line to separate the two classes, and depending on what value it takes, it'll tell us which class we're in. So the limitation of linear discriminant functions is that they can only have a linear decision boundary. That green line between the two classes can only be straight, can't have a curvy line. And unfortunately, most problems that we come across, you need to have a curvy line, not a straight line, because they're not linearly separable. But the support vector machine makes a non-linear decision boundary, a curvy line, and it uses a linear model to implement it. So that's sort of how does it do that? That's like a really bizarre thing to do. So the trick that it does is by transforming the data points with a non-linear function into this feature space. So they have so they separate the data points in the feature space with a linear decision boundary, a straight line. But because we've taken a non-linear mapping, back in the data space, that straight line is actually curved. So let me show you a picture. So here on the left-hand side, we've got our data space, and we're trying to separate the circles and the crosses. And we can't do it, we need a curved line. So we transform the data into a feature space. So look, I've shown it here as two-dimensional again, but you have to imagine that it's in a much higher dimensional space. And in that much higher dimensional space, we can put a linear discriminant between the two different classes. And if you think back to the Cursed Dimensionality work that we did several weeks ago, you can sort of see why you could get a straight line between the classes in this higher dimensional space. Anyway, so in the feature space, we can use a linear discriminant function to separate the classes, and when if we were to map that straight line back into the data space, it turns out that it's curved, and that's because we're doing a nonlinear mapping between the data space and the feature space. Let's look at an example of a feature space. So let's pretend that we've just got two attributes in our data space, x1 and x2. And we're going to make, instead of having just 2 dimensions that we have in our data space, we're going to have 4 dimensions in our feature space. So x is our data space, a is our feature space. And we're going to do it in sort of a polynomial way. So in our feature space, the first dimension we derive by cubing x1 and then multiplying by x2 to the 0, which is just 1. So the second attribute, a2, in our feature space is x1 squared times x2. The third attribute in our feature space is x1 times x2 squared, and the fourth attribute in our feature space is x1 to the 0, which is 1, times x2 cubed. So you can see the pattern that we've taken. It's just a simple kind of polynomial. So the polynomials add up to 3 in each case. So 3 plus 0, 2 plus 1, 1 plus 2, 0 plus 3. So we've gone from 2 dimensions in X space and our data space to 4 dimensions in our feature space. So what a line looks like in our original data space would be like this first equation. So y equals w0 plus w1x1 plus w2x2. So that's just it's just a line. And if we had a line in feature space, then we would have y equals c0 plus c1a1 plus c2a2 plus c3a3 plus c4a4. So it's just a constant times the attribute value. Now if we go and replace the a values back with the x values, you can see that the line in the feature space is if we think about it in terms of the data space, it's a polynomial. So it's c0 plus c1x1 cubed, c2x1 squared x2, c3x1 x2 squared, and c4x2 cubed. So you can see it's curved. So a straight line in feature space is a curved line in data space. So there's two problems that you could think about if you do this kind of mapping. The first is computational complexity. So you can see that we've gone from 1, 2, 3, W0, W1, W2, so 3 coefficients or parameters in the data space, to 1, 0, 1, 2, 3, 4, 5 coefficients in the feature space. So because we've got more coefficients or parameters, it's going to be much more computationally difficult to work them out, for the learning algorithm to work them out. And if there's too many coefficients for the amount of training data, then we run into our old mate, overfitting. So support vector machines manage to solve both of these problems of computational complexity and overfitting in quite a clever way. And the trick is that they use a very special kind of linear model, and it's called a maximum margin hyperplane. And this is the hyperplane that gives the biggest or the greatest separation between the two classes. So remember we were talking before about finding the hyperplane that maximizes the minimum distance between the data points in the hyperplane, and the other approach was to separate the data points by the widest margin. That's what this is. This is the maximum margin hyperplane. So trying to drive the widest road between the two classes. So let's sort of see how it works. So we're going to assume that the data set has just 2 attributes plus a class type, and we're going to assume for the moment that the classes are linearly separable. So we can relax that last constraint a bit later, but for the time being, let's just assume that they're linearly separable. So our data set looks something like this. Now what we're going to do is we're going to calculate the convex hull of the two classes. So the convex hull is just the line that surrounds the points. So think of these little data points as sheep. We want to put a fence around the sheep, and we want to put the smallest fence around the sheep, assuming the sheep don't wander around. And because the classes are linearly separable, the convex hulls don't intersect. So if we do that, we get something that looks like this. So you can see we've got a fence around the blue points and the fence around the red points. So the maximum margin hyperplane is the line that's the furthest apart from each convex hull. So it's the line that separates the data points with the widest margin. So it looks like this. So you can see here that the distance from the shortest distance from the green line to the blue fence and the distance from the green line to the red fence is as wide as possible. It's It's the widest road that you can drive between the two fences. Another way of saying that is that the maximum margin hyperplane is orthogonal, or 90 degrees, to the shortest line connecting the hulls. We'll see that that's a dotted line in a moment. And the data points that are at that minimum distance to the hyperplane are called the support vectors. And there's always at least one per class. And it turns out that the support vectors are the only data points that are important to the classification problem. So they're the only ones that affect where the hyperplane goes. So you can see here, we've got our convex hulls. We look at the dotted line goes across the margin, and we're looking at the starred data points are the data points that are the closest, the minimum distance to the hyperplane. You see in this case we have 3, and they're called the support vectors. So they're the only data points which describe where that green line goes. The other data points can be anywhere else on the graph, as long as they don't become support vectors. So they can't be closer to the green line. So this is quite an important concept. So only the support vectors are the only data points that define where that hyperplane is going to go. Before we wrote the line as y equals w0 plus w1x1 w2x2, and so w1 and 2 were the values of the weight vector, and w0 was our bias. We write it slightly different with the support vector machine, and typically it looks like this. So y equals b, so that's essentially the bias, and then we have a sum over all of the data points that are support vectors. So we don't care about any of the other data points, only the support vector data points. We multiply alpha I is a parameter that we're going to, that's associated with the data point I, support vector I, and we need to, the learning algorithm needs to find that. Zi is the class, so that's either +1 or -1. And the bit in the brackets here, xi, is the ith support vector, and the dot product of that with x, which is the line that we're looking at. So the new data point we're going to test. So the task of working out where this maximum margin hyperplane goes comes down to working out which data points are support vectors and which one, and what the b and the alpha values are. Now it turns out that, let me go back here. The kernel function typically comes into this second bracket here where we have that dot product between the xi and the x. So usually that's kernel function of xi, x. But we're assuming the linear kernel function in this case, just to make things simpler. So we need to work out the alpha values and the b and which ones are the support vectors. So it turns out that this ends up being a problem in a standard class of problems called constrained quadratic optimization problems. And these kinds of problems are convex, which means that there's no local optima. This is excellent because it means that there's special algorithms that we can use to solve those kinds of problems really efficiently. And we're not going to go into those, but it's a standard kind of problem to solve. Overfitting is unlikely. So overfitting is associated with instability of the classifier, i.e. if we add or delete data points, that causes big changes in the decision boundary. So we know that that's variance. A large part of the error the error is caused in large part by the variance. But the maximum margin hyperplane is relatively stable because it only moves if the support vectors change. It doesn't care about many data points, it only cares about the support vectors. So if there's only a few support vectors, then it's resistant to, it doesn't have a huge component caused by the variance. So we can think of the support vectors as global representations of the entire data set, but the fact that there's only relatively few, therefore it's not as flexible learning algorithm, which is good in this case. Computational complexity, so this is still a problem because every time we need to classify an instance, we need to calculate the dot product with all of the support vectors, which is one add and one multiply for each dimension. So it could be quite a problem if we have high dimensional data. But it turns out that we can use a special trick called the Kernel Trick. So we can calculate the dot product before we do the nonlinear mapping. So we don't need to do that nonlinear mapping. So we're defining a kernel function that's the dot product of the xi and xj after they've been projected into the phi space, into the feature space. But the support vector machine only interacts with the data through the kernel function, so we only need to use this kernel function. So we saw those before. So the first one is the linear kernel, where we just take the dot product. Gaussian or RBF, radial basis function kernel, we saw before. Another kernel function is another common kernel function is a polynomial kernel, which just raises so it takes the dot product, adds 1, and then raises that to the power h, which is the size of the larger size of the polynomial. We assumed before that the data was linearly separable. If we do that, then we end up with something with a support vector machine called a hard margin support vector machine. And so it can only classify linearly separable data. But most of the time, our data isn't linearly separable, so we need to relax things a little bit so that we can deal with data where data points sort of fall into that margin by some amount. And so what we can do is we generalize support vector machines to be something called soft margin support vector machines. And we have an upper bound on the values of the alpha I. And if we do that, then it's called a soft margin support vector machine. Essentially what it means is that it will tolerate a certain number of errors or a certain fraction of errors. Most of the support vector machines you would use would be soft margin. There wouldn't be any, you really wouldn't use a hard margin support vector machine. Support vector machines originated from research into statistical learning theory by Vapnik in 1995. They tend to be slow to train, and you'll see that in KNIME when we play with them, but they tend to be quite accurate. The complexity of the classifier is based on the number of support vectors, not the dimensionality, which is a really interesting idea. And this is what Vapnik was looking at with the statistical learning theory. He was looking at trying to find bounds on error based on that weren't based on the dimensionality. So we can use the number of support vectors to calculate an upper bound on the expected error rate of the support vector machine, which is independent of the dimensionality. So we can do support vector machines in Rattle and R. So we'll see that in a moment, and we can do them in KNIME as well. So let's first look at the nodes that you would use in KNIME. So there's several approaches here. The first, SVM learner and SVM predictor, are probably the easiest ones to configure. You can choose between several different kernel functions. So that these are the nodes. There's also libsvm learner and libsvm predictor, and they allow you to they end up calling something called the libsvm library. So several years ago, this libsvm library was developed in, I think it was in C or C++. And it's a very standard library that people use for support vector machines. So this libsvm learner calls that library. It's a little bit more difficult to set up, but it has more parameters that allow you to use them. There's also, like there was with Random Forest, there's a Weka node for support vector machines. Let's look just quickly, for those of you that are using Rattle, we'll just look quickly about how we can do that. So the support vector machines are in the model tab. Under the bonnet, Rattle's using something called KSVM. KSVM is the package in R Kernel is a package in R, and KSVM is the support vector machine algorithm within that kernel. It's very, very comprehensive, quite powerful. It can do a lot more than what Rattle shows it to do. And you can select several different kernels, so radial basis kernel is as useful as anything. The other good thing is that with the radial basis function kernel or the Gaussian kernel, you need to set the sigma value, and it can be quite sensitive to the value of that parameter, and it might be hard to set. So what's nice in Rattle is that it automatically finds the value for the sigma parameter for you. This is just a screenshot of the support vector machine page within Rattle. In this case, we're using the polynomial kernel for degree 1, which would be the same as the linear kernel. And you can set different parameters in there. That C equals 10 is a way to specify the softness of the classifier. And when you run the classifier using the execute tab, then you get this kind of output. So CSVC is the standard regularized support vector classification. So C is the penalty or the cost parameters. So high C allows you to misclassify more data points. This is the part that automatically finds the value of the sigma parameter for the RBF kernel. This next line tells you how many support vectors were chosen. So in this case, it was 106. And this last line here, the training error, tells you the because remember it's a constrained quadratic optimization problem. This objective function value tells you what the minimum value was. Training error tells you the error on training set. So that's it for this week. I'll see you in class.